Hello everyone! My name is Joanna Piotrowska and I'm a final year PhD student at the University of Cambridge. Today, I'd like to share with you the results of a recent project where we use machine learning to identify physical processes responsible for quenching in massive central galaxies. To start us off, let me remind ourselves that galaxies in the observable universe can be divided into two broad categories: blue star-forming and red quiescent. Blue galaxies are typically dominated by young stellar light and show a lot of structure with gas, dust, and active star formation. On the other side of the galactic scale, the red quiescent galaxies are typically characterized by smooth light distributions with little to no gas and dust, dominated by old stellar populations. These two galaxy groups are interpreted as an evolutionary sequence in which blue star-forming galaxies transition to become red in a process called galaxy quenching. Now that we know what quenching is, let me highlight two main takeaways from this talk. These are: A. Black hole feedback is the most likely cause for central galaxies ceasing star formation, and B. It is the integrated history of AGN feedback rather than the instantaneous activity of the AGN which ultimately determines the star-forming state of a central galaxy at redshift 0. As means of introduction to our project, let me highlight that over the past 2 decades, quenching has been shown to correlate with a range of galactic properties, such as stellar mass, the more massive you are, the more likely you are to stop forming stars; galactic environment, the higher the local density, the higher the chances of satellite galaxies being quenched; galaxy morphology, the more prominent the bulge, the more likely the galaxy is to be quiescent; and, most recently, the higher the mass of a supermassive black hole, the more likely the galaxy is to be quenched. All of these observed correlations between galactic properties and quenching are an observable consequence of physical processes which prevent galaxies from forming new stars. Ultimately, the universe can go about it in 2 ways, either by removing star formation fuel, no gas, no stars, or by decreasing the efficiency with which the available gas collapses under gravity. As of today, the fuel route enjoyed a fair share of observational support for processes which either drive the gas out of galaxies or prevent cooling and accretion of gas from galactic halos. On the other hand, processes governing star formation efficiency have seen less observational evidence, and a broad range of different mechanisms has been proposed from a theoretical perspective. This brief summary highlights the complex landscape of galaxy quenching research, where multiple different avenues are competing for the title of a primary driver of quiescence. Embracing this complexity and disentangling the most important physical process responsible for shutting down star formation is the focus of our work, where we investigate intrinsic quenching mechanisms operating in massive central galaxies. In order to do that, we set up an experiment in which we take the output of 3 cosmological simulations, Illustris and IllustrisTNG, and compare them against the observations as seen by the Sloan Digital Sky Survey. It so happens that all 3 simulations implement different prescriptions for their AGN feedback mechanism. Hence, using all 3 simulation suites, we can extract theoretical predictions for the observable consequences of different AGN feedback quenching mechanisms. In order for our experiment to succeed, we need to make sure that the observable universe is quite well approximated by cosmological simulations. Here I'm showing you the mass star formation rate plane for simulated and observed galaxies, and as you can tell, both the simulated and the observed ones occupy a similar locus in the mass star formation rate plane. Galaxy distributions also show a split between star-forming and quenched populations. However, it is worth noting that in both Illustris and IllustrisTNG, the quenched population is exclusively at higher stellar masses when it comes to central galaxies. This is also a good moment to define what I mean by quenched, and whenever I refer to things as quenched in this talk, I will mean that their measurement of specific star formation rate is less or equal than -11 in logarithmic units. In order to move on with our experiment, we identify 3 most important processes that we think are relevant for quenching star formation in massive central galaxies. These are black hole feedback, virial shock heating, and supernova feedback. And for each of those processes, we also assign a measurable galactic parameter that is most closely related to the process of interest. For black hole feedback, it is black hole mass, halo shock heating, halo mass, and for supernova feedback, that is the total stellar mass. In simulations, it is easy to extract all 3 parameters directly from the simulation snapshots. However, in observations, the situation is a little bit less straightforward, especially with the measurement of black hole mass for Sloan. Luckily for us, there exists a range of correlations between dynamically measured black hole mass and galactic properties, among which the one between black hole mass and central velocity dispersion is the tightest. Hence, in our research, we use a range of calibrations between MBH and sigma star in order to estimate black hole masses in Sloan. Coming back to my previous slide, I would like to once again highlight how complex the landscape of potential physical processes is when it comes to galaxy quenching. And hence, in order to investigate quenching properly, one needs a tool that can embrace all of this complexity. And that's where machine learning and, in particular, random forests come in. Putting our research in machine learning context, we use a supervised machine learning approach to classify astronomical objects. Hence, we know or decide the classification labels a priori. Within the scope of available algorithms, we choose to use random forest classifiers for a reason I will explain in a moment. To be more precise, we classify galaxies in the simulated and the observed universe into star-forming and quenched categories, feeding the algorithm with 3 input parameters: black hole mass, halo mass, and stellar mass. A random forest, and a classifier specifically, is a collection of binary decision trees, which combined with bootstrap random sampling, learn to predict classification probabilities using a set of provided input features. A single decision tree is a set of binary splits or nodes on a dataset, where each split is optimized to minimize the impurity or inhomogeneity of the resulting daughter nodes. The splits are performed by choosing a boundary value in one of the input features, and the algorithm always chooses the feature resulting in the best split possible. There are different ways in which trees decide on the optimal split, and in our research they minimize Gini impurity, which measures how often an object randomly drawn from a daughter node would be misclassified. The trees proceed to grow until they reach user-defined conditions, or until every object finds itself in a separate leaf node, which is usually not a welcome case. As I mentioned before, a forest is a collection of multiple such trees, each of which is supplied with a subset of the input data bootstrap sampled with replacement. An example of such one tree in our forest is presented in the slide, showing how the node purity increases as the tree grows. In case you're wondering whether or not to use machine learning, and random forests in particular, in your research, let me tell you why we decided to use them. First of all, they are straightforward to implement. Straightforward enough, in fact, that some time ago I put up a simple tutorial on how to apply them to the SDSS data, and you can find that on my GitHub page. Second of all, random forests are incredibly intuitive, and since we can easily follow the logic of decision trees, they are no longer a black box approach, often feared in the research community. More importantly, due to their simple architecture, random forests allow us to extract information about which input feature holds the most predictive power in determining the classification. This allows us to tease out physical mechanisms most likely responsible for quenching in massive central galaxies. Finally, as has been recently shown empirically by Ace of Luck, random forests are capable of correctly identifying causal relationships between classification labels and input parameters, which aids in resolving the long-standing problem of correlation not implying causation. In the slide, I'm presenting the results of our random forest classification for simulations on the left-hand side and observations on the right. What I'm showing here is the relative importance of each input feature, black hole mass, stellar mass, and halo mass, for determining the final star-forming quenched classification. What you can see in the left panel is that all 3 simulations, Eagle, Illustris, and IllustrisTNG, agree that it is the black hole mass which is the most important parameter for determining the classification. And this is true regardless of the exact details of the implemented AGN feedback model. If we then move on to the observations, we see that this theoretical prediction is matched extraordinarily well in the SDSS, where this result is insensitive to the exact choice of the black hole mass calibration. In simulations, we can go a step further and add a black hole accretion rate into the mix. In the slide, I'm showing the result of the random forest classification for simulations only, this time using black hole accretion rate as an additional parameter. What you can see is that black hole mass is still the most important parameter for determining the final classification, and black hole accretion rate is irrelevant in comparison with black hole mass for all 3 simulation suites. When we then look at the distribution in black hole mass bottom panel and black hole accretion rate top panel between star-forming and passive galaxies in all 3 simulation suites, we can immediately see the differences between all three feedback prescriptions. In the top panel, we can see how Eagle, Illustris, and TNG predict different relationships between the star-forming state of the host and the instantaneous AGN activity. In the bottom panel, on the other hand, you see that more massive black holes are usually associated with quenched objects across all three simulations. In the final part of my talk, I would like to focus on the operational mechanism of quenching in massive central galaxies. In order to do that, we focus on the molecular gas content of galaxies, starting with the simulated ones in Illustris and IllustrisTNG. In this slide, I am showing the specific star formation rate, top panel, gas fraction, middle panel, star formation efficiency, bottom panel, as a function of black hole mass in Illustris, left-hand side, and TNG on the right-hand side. If you focus on the top two panels, you will see that both simulation suites show qualitatively similar trends in which both specific star formation rate and gas fraction decrease as a function of black hole mass. The decrease in gas fraction in Illustris is slightly more dramatic than it is in TNG, however the overall trends are the same. When we then focus on the bottom panel of star formation efficiency, we can see that Illustris galaxies do tend to be more efficient at forming stars at higher black hole masses, while in TNG, the trend remains roughly flat to then collapse around 10 to the 8 solar mass. In order to compare the simulations with the observations, we need to add several layers of observational realism, and we do that by restricting the simulations to SDSS-like fiber apertures, imitating signal-to-noise ratio cuts on emission lines, and adding measurement uncertainty as one seen in the SDSS. The result of all of these operations is presented here on the slide, where we've got the exact same quantities: specific star formation rate, top panel, gas fraction, middle, star formation efficiency, bottom panel, all as a function of black hole mass for SDSS in the leftmost column and Illustris and TNG in the next two columns. This time I am also overplotting the simulated result on top of the SDSS to have a better visual comparison of the exact trends. I would like you to focus your attention on the bottom two panels showing gas fraction and star formation efficiency. If you look at the gas fraction alone, you will see that both Illustris and IllustrisTNG show agreeing trends with decreasing gas fractions as a function of increasing black hole mass. The same trend is reflected in the observations in Sloan, hence both simulations qualitatively agree with the observations. When we look at the star formation efficiency, however, the story is somewhat different. We see that treating Illustris galaxies with these three simple steps of observational realism leaves behind a visible trend of more efficient star formation at higher black hole mass, which is in direct contrast with the TNG galaxy population, which shows a relatively flat star formation efficiency profile as a function of black hole mass, which then turns over at the highest masses. This trend agrees qualitatively better with the SDSS, however, neither of those is a perfect match. If we then repeat the random forest experiment, asking the algorithm to classify galaxies into star forming and quenched, but this time feeding it information about star formation efficiency and gas fraction, we can see that in the SDSS, star formation efficiency holds more predictive power than does the gas fraction. Similar trend is seen in TNG, while in Illustris it is exactly reversed, where all of the quenched star forming classification is purely driven by the gas fraction as estimated within the galaxy. This difference seen in the molecular gas behavior between the simulations is a consequence of the differences in the implemented AGN feedback prescription. At high accretion rates in Illustris, black holes inject thermal energy into their immediate surroundings in the so-called quasar mode feedback. At low accretion rates, on the other hand, the simulations inject kinetic bubbles at large distances around the galaxy, aiming to capture the effect of interaction between radio jet lobes and the intergalactic medium. In TNG, the quasar mode is very similar to that in Illustris, however at low accretion rates, the AGN act locally, injecting momentum kicks in random directions around the black hole particle. By comparing the molecular gas trends among IllustrisTNG and the SDSS, we conclude that a viable AGN feedback model should combine heating and turbulence injection in order to successfully quench star formation in massive central galaxies. Before we say goodbye, I would like to summarize my talk in 3 highlights. First of all, we use machine learning analysis to find that black hole mass is the most important parameter for determining whether a galaxy at redshift 0 is star-forming or quenched, and this result is true in all 3 investigated simulations, regardless of the AGN feedback implementation, while in the observations, it is true regardless of the calibration used to infer black hole mass. Our random forest analysis also shows that black hole accretion rate is an irrelevant parameter in comparison with black hole mass in determining the final star-forming quench classification. By comparing the molecular gas content between the simulations and SDSS, we conclude that a viable AGN feedback prescription most likely combines heating with turbulence injection in order to successfully prevent future star formation in massive central galaxies. Thank you very much for your attention. In case you have any questions, you can reach me via Slack or at the following email address. I am really looking forward to meeting you online and hope you enjoy this action-packed week of conference. Do zobaczenia!